So do you guys recall the changes of state? Okay. What we call those different phase changes. And then whether those phase changes are endothermic or exothermic. Okay. What does it mean to be endothermic? Your system or your substance is absorbing heat from where? Always the surroundings. There's only two things. There's only two objects in thermodynamics. There is the system, and then there is the surroundings. And we get to choose what our system is. And in chemistry, we choose our system to be typically what? A chemical reaction or a specific phase of matter, a specific substance of matter. That's our system. Okay. So when we, for example, and this is the one we're going to focus on first today. Okay. When we vaporize a substance, so I'm talking about vaporization. Yeah. That's a phase change between what and what? Liquid is becoming gas. What's the difference between solid phase, liquid phase and gas phase? One of the differences that we talked about yesterday, especially the amount of kinetic energy in them. Now, for a specific substance, that's a unique amount. But in general, a gas has way more kinetic energy than a liquid does. What is the temperature at which this vaporization happens known as? We call it the boiling point, right? Okay, and we are going to talk more today about what boiling very specifically means, because it means something intentional. But let's think just about vaporization to begin with. Let's start with that. And then we're going to get into some other phase changes. So let me get back to where I was trying to be. When we go from liquid to gas, if this process happens, right, in an open container, okay, so I just have some water in an open container, right? Eventually, what will happen to all of this water? Eventually, it will all evaporate. Okay. Why will it be slow here at room temperature? Yeah, we're only transferring a limited amount of heat from the surroundings to this system, right? Where does water evaporate from, or any liquid? Where is it evaporating from first in this beaker of water? Is it evaporating from the bottom? It's the surface, right? Okay. Do you believe me that all liquids at their surface are always evaporating a little bit? Pretty much, yeah. I mean, we can talk about different temperatures and stuff, but I mean, that's the thought, is that no matter what the temperature, the liquid at the surface is being evaporated. That is why what? Even though this is room temperature, all of this water will eventually what? Evaporate away. Okay. What I want to focus on is what if, let me make sure I just said all the right things. What if we're in a closed container? Okay. What if we're in a closed container? I'm not ready to pull that over, not just yet. Do I still have liquid turning into gas? Yes, that's a thing. But what happens? Some of it turns into gas, and then what happens? I know y'all can't see this, but I know you know what should be visualized right here. At the top of this closed bottle of water. What do I see on the lid? Here at the top. Who said what? Condensation. You see the condensation? Can you like carefully pass it around so you don't knock it all down, Robert? Okay. Guys, there's condensation. What is condensation? The physical process of gas going back to liquid, right? In a closed container, there is, y'all remember this arrow sign? Y'all recall that maybe from Gen Chem 1? The double arrow, the back and forth. This double arrow, when I taught it to you, at least in my class, when I first introduced this double arrow, it's usually talking about weak acids or weak bases. And I said, that means there's like a back and forth. Well, yeah, that is still what this means. But more specifically, the word that this means is equilibrium. We're going to devote 3 whole chapters to equilibrium in this course. A lot. So I'm not getting into it right now. But equilibrium doesn't mean there's equal amounts of liquid and gas. Look in that water bottle. John, is there equal amounts of liquid water and then the little bitty condensation at the top? Absolutely not. Equilibrium means the rate at which the water evaporates equals the rate at which it does what? What's this called? That's vaporization. What's this process? The backwards process. Condensation. That's what equilibrium is about, the rate being equal. Just keep that in mind for when we get to further chapters. Equilibrium is not about amounts being equal, it's about rate being equal. But you guys can see that in the water bottle, right? Some of the liquid at the surface vaporizes, and then that gas condenses back down to liquid. That's why we see the droplets. What do we know gases have that liquids and solids do not have? There's a particular property that gases have that liquids and solids do not have. Say it again. It is pressure. That's correct. Guys, gases have a pressure. When we're talking about the gas at the surface of a liquid, that is known as measuring the vapor pressure. Vapor pressure. It's not, so what is vapor pressure? It's not just any old gas. It's specifically the pressure of gas where? In a what kind of container? It's got to be closed. Otherwise, we can't measure it. Okay? Otherwise, we can't measure the pressure because it's escaping, right? Can't get it. So sometimes we'll just write P. Sometimes we may be a little more deliberate and write P, vaporization. But in this section, I'm talking about vapor pressure. That's the only pressure I'm talking about. Okay, vapor pressure. Okay. What do you think can influence how much vapor pressure a liquid has? Okay, I like that. That's a pretty good thought, is how much volume in the container there is. But let's assume all things are equal. Sure, whatever temperature is at, absolutely can affect. How would temperature affect vapor pressure? I'm not saying that volume, let me just reiterate, volume absolutely would play a role. That's yet another aspect to it that in this course, we don't we don't try to take into account. In more upper level chemistry courses, we do take that into account, but not so much right now. You guys tell me, how would changing the temperature change a liquid's vapor pressure? What do you suspect? Okay. We increase the temperature, we get more this way, right? And more gas above the surface means a higher vapor pressure, right? Very good. Higher temperature, higher vapor pressure. Something else? Kind of our main focus of our talk yesterday. What are those things called? IMFs. I'm just like super deaf today. I don't know what's going on. Part of it is the fan, and then just my ears are plugged up. I don't know. So yeah, IMFs, right? What do IMFs? The gas, right? The gas is the phase that has the IMFs, right? Now I'm messing with you now, right? That's not true. Why do gases not feel those IMFs? Too fast. Too fast. Too much kinetic energy. It's the liquid that you got to look at. What kind of IMFs does this liquid have? Because here's the surface, right? The more IMFs, the harder it is for those molecules to what? Evaporate off, right? IMFs, Velcro, stick together. Stronger IMFs mean what then? About vapor pressure. A larger value or a smaller value? Smaller. Everybody hear that? Less gas, less pressure. Those are two main concepts for first half of class today. Change the temperature, change the IMFs, or compare the IMFs, you'll see differences. So I want to look at a couple differences. Look on your in-class examples. Okay, we just answered number 5. What is vapor pressure? What factors influence it? But now I've got 4 compounds listed. These, except for water, are compounds that I certainly did not get a chance to cover in my Gen Chem 1 class. These are organic compounds. We are going to talk about organic compounds at the end of this class, Gen Chem 2. So you may not know that the formula of this compound called ethanol contains what? Can you guys look on your sheet? How many carbons does an ethanol have? 2. How many hydrogens? 6 total, and then an oxygen, right? And the way it's bonded together, I would not expect you to necessarily know that at this point. Okay? I don't expect you at this point to know that that's how ethanol is bonded together. What I do expect, and this is what we were, Catherine, like at the end of class yesterday, whenever we were talking yesterday. And I said, what I really want is for you guys at this point to learn to look at a formula and know a couple of like hacks, little shortcuts. Yeah.
So, not so suggestive, but to have hydrogen bonding, you're going to have a dipole, right? Because you can't have, or can you have,
has to have dipole. Yeah, has to be a polar molecule. So one of the hacks that I want you to look at is if I give you a formula, like this, regardless of you understanding what it actually looks like in 3 dimensions, which looks like this. Okay. Carbon, carbon. Hydrogen's on the carbon, but the carbons are bonded to each other, right? And then that carbon is bonded to an oxygen. Okay. Guys, I just need you to recognize that if you have an oxygen and a hydrogen in a group like that, A, that means that compound is polar. Why? Guys, that shape of that oxygen right there is never going to be symmetrical no matter what is attached to it. It's not symmetrical, it's polar, right? And not only is it polar, which means it can have, y'all tell me, what kind of IMFs can this compound have? Ethanol. All three, basically, right? Everything can have, y'all probably can't see that. Let's do this. Everything can have IMFs, right? Everything can have LDS. Let's try that. Because it's polar, it can also exhibit dipole-dipole with other molecules, right? And because it has an OH specifically, it can hydrogen bond with other molecules that have, what are the three elements? N, O, and F. Okay. Let's keep looking down the line. Ethylene glycol. I'm not going to draw all of these up here on the board because we have them drawn already. But when you look at ethylene glycol, what can you now tell me about what kind of IMFs it has? All of them as well? Sure. Everything has LDS. Why is that obviously polar? Okay, you guys, this is where you do have to have a little bit of knowledge about shape. Why is this polar? The way I have it drawn up here, okay, sure. Is everything around that oxygen symmetrical? Around that oxygen, is that symmetrical? This is not, what if I do it like this or this? This is not symmetrical. It's not symmetrical. Polar. Dipole-dipole. Because it has OH, it can what? Hydrogen bond. And guys, why is this one even more special compared to the ethanol? Double places it can hydrogen bond, right? Double ability to hydrogen bond. Next one.
Okay, so could you also tell that it's polar by just the OH? Or
yes.
Okay.
Yes. OH means it's polar. We'll see when we get to talk about a little organic stuff. The more other crap it has on it may make it really not great polar, but it is still polar. Yes. Okay, I didn't have quite enough whites to fill in all of my hydrogen, so I'll just pretend. But okay, here's the next one. Do you guys know what ethylene glycol actually is? Y'all know what this is. You just don't know that this is what it's called. This is what's an antifreeze. Buy antifreeze for your car. This is what's an antifreeze. Okay. Yeah. Okay. And ethanol, right? Ethanol is an alcohol. This is the one that you can drink. There's other alcohols that you should not drink, like isopropyl alcohol or methanol or other things, but that's the one that you can drink. Diethyl ether is actually originally used as an anesthetic. People would take this and they drop it on masks and knock them out, or I mean, it's kind of addictive also because it gives you like a euphoria and okay, anyways, whatever. So it's also highly flammable. Like it catches on fire like nothing. So we don't use it anymore as an anesthetic in operations. But when you look at this shape right away, you guys should be able to tell me, is this polar or non-polar? Because of the O. Polar because of the O in the middle. Because what is on the other side of this oxygen? It's not drawn. Lone pairs. Lone pairs. And lone pairs are not equivalent to these bonded things. It's not symmetrical. Polar. Because of the oxygen. What kind of LDS? On your paper, right? Diethyl ether. It can have dipole-dipole because it is polar. And it will also have LDS. But no hydrogen bonding here, right? Why? There's not an H directly bonded to that oxygen. So there is no hydrogen bonding possible. Last one, which we talked about yesterday, water. What does water have? All the things. All the things. And in fact, do you guys even remember me telling you about, right, water can really H bond like spider webs. It can H bond a lot, right? Okay. So now I want you to rank these four. And ranking is sometimes kind of good. You gotta be clear how you word it. How did I word it in the problem? Predict the relative vapor pressures. Okay, so what I'm saying is let's rank them. When I say let's predict, I don't need a number. I want to rank. So let's do, yeah, so let me think. How did hang on, I got to see how I did it on the slide so I match what I said. Which one of these four should have the highest vapor pressure? We're assuming everything's at the same temperature. I'm not talking about temperature. We're really just looking at the effect of IMFs. Which one of these four should have the highest vapor pressure? I hear that. I hear that. Remember, what you're thinking to yourself is which one of these four is most easily going into gas phase. The easiest to go into the gas phase has the highest vapor pressure, right? But these are liquids. These are liquids. Which one has, so we wrote this statement, maybe we need to write the inverse statement. What's the inverse statement of this? Weaker IMFs means larger vapor pressure. Okay, so now that we got that straight in our heads, maybe, which one of the four should have the highest vapor pressure? Joseph's been saying it. Y'all, some of y'all have said it too, and then you were like, no, she's trying to trick me. It's the ether, guys. It's the diethyl ether. Why? It can't H bond. All the other three can H bond at least some, maybe more than some, but that ether can't. Okay, so ether. Then, what next? Loretta says ethanol. I like that answer. What do you guys think about that answer? And can Loretta, you explain why you think that's the answer? I think you're trying to say the right thing, but your wording is not the right words to use. Are you trying to say? So we're looking at the correct one, right? You're looking at ethanol? Ethanol, the very first one right here, right? I knew that's what she was. I knew that's what she did. Okay. There we go, guys. Look at that ethanol. It has an OH. It can only H bond with that one H that's right there. Y'all see what I'm saying? As what we know is going to be different about these other two. Okay. So the next lowest, no, sorry. Is that the right way to say that? Whatever. Ranking wise, we're going down. Ethanol has a lower vapor pressure than ether. Okay. Now, Let's think. Let's think. Here's my ethylene glycol. Here's my antifreeze. Here's my water.
Well, it's a larger molecule, so it will have a higher LDF or dispersion forces. So
Okay. Both of these compounds can hydrogen bond twice. Let's just say. Both of these compounds have two hydrogens that can H bond. So that's equivalent. So you got to go down the list. We didn't really talk about any specific differences for dipole-dipole between molecules, and we're not going to. But we did talk about differences for LDF strength based on what? Size and perhaps surface area. And so between these two, which is the bigger size, ethylene glycol. So this guy can double hydrogen bond. It's big fat molecule. Guess what it has? The absolute lowest vapor pressure. You see how we went through the thought process.
So that means that size and vapor pressure are interrelated.
Say it one more time.
Size and vapor pressure are interrelated.
Can you say that size and vapor pressure have an indirect relationship? All other things being equal, yes. In fact, maybe you guys can see, I don't know actually that you can. I had put these 4 compounds out here in covered jars. And if you just look down on them, you can, I believe, tell that the ether has more condensation clinging to the lid. Why? Because it's going into the gas phase more. And if you look at these and the ethylene glycol, there's 0 condensation up here on the lid. I'll move these over here if y'all want to look at them when you walk. Take a break later. You can. All right. So I said we were going to talk about what does it mean when we say boiling point, because if we take this liquid, any of these liquids, to their boiling point, they should do what? They should vaporize. They should turn into a gas. Yes. But boiling points can be different for a substance under different conditions. You guys might recall this from Gen Chem 1. We talked about it a little bit. Do you guys recall what it is that determines the boiling point of a substance? Nobody can remember? I wish I had grabbed this thing. It's fine. I'll do it. So the temperature, no, and that's a really good guess. The heat capacity is a good guess. The temperature is what it goes to when you know, measure the kinetic energy, or you add heat or you take away heat. That's not really what it is. Think about trying to escape, right? What pressure? It is. Okay, let me put this up on the screen. Boiling point. The boiling point of a substance is the temperature where vapor pressure of the liquid equals the what? The atmospheric pressure pushing down on the surface of the liquid. That's boiling point. So now we need to recall something about atmospheric pressure. First of all, with boiling point, I personally will sometimes just write BP, and that's, I mean, boiling point. Sometimes I will also write T with a B there, that again, I'm talking about boiling point. Okay. It's the temperature, right? Where vapor pressure equals atmospheric pressure, right? We need to know what this word normal means, because this word is going to be used a whole lot right now. Normal means one atmosphere of atmospheric pressure. That was the unit most of us used in Gen Chem 1 when we did ideal gas law. We used atmospheres. In this particular chapter, we can use other units. Y'all recall another unit that we used back in Gen Chem 1 with gases? There's another unit we used a lot, and we got it from measuring a column of mercury in a barometer. MMHG. And then now this other one is pascals. And we did not, at least in my Gen Chem 1 class, we didn't use it a whole lot. We are going to use it a lot here. Sorry, excuse me. What is normal in millimeters of mercury? A value of 760. Okay. What is another equivalent unit that sometimes gets used instead of millimeters of mercury as the name of it? Yeah, that's the one. Torr. Those are the same thing. Okay. And now, this unit we'll see a lot in this chapter. Kilopascals. So a pascal is a pressure unit. Kilo is the prefix, a kilopascal. A kilopascal normal is 101.3 kilopascals. Okay. So normal boiling point. Right? If we say this is the normal boiling point, it's the temperature under standard atmospheric pressure. You guys should already know this value for water. 100 degrees Celsius, right? That's the only value I think you have to know. Yeah, another value I'd have to tell you, but you guys should know water, normal boiling point is 100 degrees Celsius. Yes. Okay. If you look at those four substances that we had on a little earlier question, I gave you guys a graph. So this should be the next in-class example. Number 8. Oh, so number 7 was define a boiling point and talk about the units. Okay, so we just did that. So if you look at this graph, what is on the y-axis of this graph? Okay, I'm measuring the pressure. What am I measuring the pressure of? This would be the atmospheric pressure. In what unit? Okay, kilopascals. All right, so what is normal pressure in kilopascals? 101.3, guys. That's this horizontal dotted line right here. That's the normal. 101.3. Y'all see that? What's on the x-axis? So now I'm looking at the temperature. And then each of these curves, I'll just use that word for now, is for each of those four substances we looked at. And wherever that curve crosses the normal pressure gives its what? Normal boiling point. Estimate for me what you think the normal boiling point of that diethyl ether is. I would say that's probably pretty close. Somewhere between 35 and 40, I think for sure. What about ethanol? It's pretty close to 80, maybe 79, maybe even 79.5 degrees C. Guys, look at what's there. There's our water, right at 100, yeah? And then the antifreeze, the ethylene glycol is off the map. We can't even see it, right? Good deal. Can you guys identify, what did I ask on question? Let's say we have an atmospheric pressure of 68 kilopascals. I think that's what I said. So that would be like if we go up to Colorado, we go way up in elevation. Okay. What are we here at Kilgore, Texas? Sea level. We're standard. We're normal. But we go up in elevation, we have less atmospheric pressure, right? What's the boiling point of water in Leadville, Colorado? How do you find that? How do you figure that out using a graph like this? Follow the y-axis to what pressure did I say? 68. Oh, that's about halfway-ish between these two scales. And then I do what? Slide over to the which line? The water line is the one I'm interested in. And come down. What do you estimate it to be around? 90. I think I looked it up just to be like super pedantic about it. Sure. I thought I'd had it written down, or I actually did anyway. So it's about 90. It's a lot different than 100, isn't it? Okay. We're going to look more at this type of graph throughout the rest of this chapter. So we're going to come back again to looking at a pressure versus temperature graph. We're going to look at some other graphs as well. Okay. All right. Oh, what did I write here? My interpretation was it was around 92. Yeah, it's midnight. Right in, almost right in between those two. Okay, let me introduce you to this equation because I said we're going to do math today, right? Let me introduce you to this equation, and then we're going to take a break before we come back and actually start doing the math. My voice needs a little rest. Need a little rest on my voice. Okay, let's write down this equation. Clausius-Clapeyron. Now, guys, this is on the versions of this that we're going to actually be using. I've already given them to you. Okay. Your chapter 10 study sheet. There's two versions of this equation that you're going to use the most. So they're already written here for you. So you can copy them down into your notes. And I said, remember, you guys don't have to memorize these. Okay. In some form, you'll have them for the test, whether you write it yourself or I give it to you. Okay. But what is this Clausius-Clapeyron equation? Well, we're trying to show now a relationship between vapor pressure and temperature. That's what this equation is about, vapor pressure and temperature, okay? Will the atmospheric pressure come into play? Yes, it will. It will. Okay. Let me just put it over here and then we'll. Okay. Vapor pressure of a liquid, P vaporization, is equal to some constant A. Okay. Some number A. We can calculate what A is. We might do that a little bit. Otherwise, you have to go look it up in a table or be told what A is. A is for that particular substance. And then we're taking, what is E? Little e like that. It's called Euler's constant. It's what's known as the natural number. You guys know that pi means a number, right? What does pi mean? 3.14? Okay. Do you guys know what E means? I want to say it's 2.71 something. It doesn't matter because guess where you can find E? Right, buddy, you can find E on your calculator. Okay. So we're taking E because this is logarithmic. So it's this natural number E, right, raised to an exponent. It's E raised to a power. What is this power? Negative delta H vape. Ooh, what does that mean? Delta H vape. Enthalpy of vaporization.
Wait, what is the article?
I'm gonna get to that. It's defined on your sheet. I'll explain it here in a minute. Enthalpy of vaporization. Delta H. What is that? What is enthalpy? It's the amount of heat that gets transferred. Enthalpy is the amount of heat under constant pressure, but we're not worried about that right now. So what does it mean specifically if I say enthalpy of vaporization? What am I talking about? What is a vaporization process? When liquid changes into gas. When liquid goes to gas, what is the heat change? What do you expect the heat change to be? Do you expect the heat change to be endothermic or exothermic? To go from liquid phase to gas phase, what must have to happen to this substance? It has to absorb energy. That's how its kinetic energy changes from liquid to gas levels. When it has to absorb energy, that means enthalpy of vaporization should be what? And if it's endothermic, we learned back in Gen Chem 1, that means this number should be a what kind of value? Should be a positive number. Just real quick, just as an aside. What if you were condensing? What if you were going not this way, but that way? Yes, it would be exothermic. But more importantly, what would be true about these two numbers? What would be true about these two amounts of energy? The amount of energy it takes in to vaporize exactly equals the amount of energy that has to come out when it does what? Let's say COND, let's say condense, like that. It's the same numbers, but they have opposite signs. Because one is coming in and one is coming out. And that's representative of what law? First law of thermodynamics, right? Energy can't be created or destroyed. It only gets transferred around. Okay, so in our Clausius-Clapeyron equation, again, this is a constant value. Sometimes we need it, sometimes we don't. We're going to see when we don't. If you see that little e, that's that natural e in your calculator. And we're doing e raised to the power of negative delta H of vaporization. What is R? If you look on your sheet, I said what R is. What is R? It's that gas constant. We used a gas constant when we did ideal gas law. This is a different unit gas constant that you have to use, and it's on your sheet. What is it? 8.314. What is that, capital J? Joules. That's our energy unit per mole of substance times Kelvin. Problem is going to be these delta H values will be kilojoules. It's just what they're just always given as kilojoules. So if this is kilojoules, and I'm trying to divide by this, which is joules, then that math don't math. So that's why on your sheet I said, guys, let's just go ahead to ourselves. And yes, this is R. Let's just get in a habit. Let's just automatically use it with kilojoule units. Let's just do it automatically. What is this with kilojoule units? You just got to convert from joules to kilojoules, and that means dividing this number by 1,000. 8.314 times 10 to the negative third. Kilojoules per mole Kelvin. Just go ahead and get in the habit. Just use that number. Or if you want to write it standard, I don't care. You want to write it with all the little zeros. There, do that. Fine. It's fine. It's fine. And so if this is our gas constant with temperatures in Kelvin, what is T? Temperature in Kelvin. Do we remember how to convert between Celsius and Kelvin? Add. To get your Kelvin temperature, take your Celsius and add 273.15. This is going to give us our relationship between what? Vapor pressure and temperature. We're also going to need the enthalpy of vaporization. Sometimes we're solving for that. Sometimes we're going to be finding that. Let's take a break. And then when we come back, I'm going to show you the two formats of this equation and how to use them that are much more useful than just this version. Okay. So we're going to look at the next several in-class examples. And we'll see. We'll just see how far we